Good day, everyone. Welcome back. I hope you all have a productive week. Today, we are driving into fascinating and crucial aspect of vibration measurement, design of vibration pickups. So, we are going to have a solid understanding how these ingenious devices work in the previous sessions. Think about it. We are having vibration everywhere. Accurately measuring this vibration is essential in multitude of applications, whether it's ensuring the smooth operation of industrial equipment or monitoring the structural integrity of buildings or bridges or in the realm of seismology. For everything, this measurement process is heart of each and everything. I am Dr. C. Sandamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. Welcome you to this new lecture video, Design of Vibration Pickups. We are going to explore how seemingly a simple mechanical system, a mass suspended by a spring and a damper, can be ingeniously used to measure the velocity of a vibrating body. Imagine this box representing casing of your transducer, which is attached to the vibrating body, whose motion we want to analyze. The vibrating body has a displacement y of t and its velocity, which we want to aim to measure, is given as velocity y dot of t equal to omega y cos omega t. Inside this transducer, we have a seismic mass m suspended by a spring with stiffness k and a damper. When the base of the transducer vibrates, seismic mass also will move, but its motion x of t will be different from the seismic mass. That is, there will be a relative motion exist between them due to because of the damper and stiffness. We particularly interested in this relative motion between the seismic mass and the base, which we define as z of t. The relative velocity z of t is often sensed and related to the input velocity omega y. Through the principle of vibration analysis, we can derive the expression for this relative velocity z of t in response to the base velocity y dot t. As you can see here, the magnitude and phase of relative velocity z of t are dependent on several factors like r and damping ratio, where r depends upon omega, that is frequency ratio, also the natural frequency, the amplitude of the base displacement and excitation frequency as well. Now, the magic happens when we design this transducer such that the term, that is the denominator, is approximately equal to 1. This condition is typically achieved when the natural frequency omega of the transducer is significantly lower than the excitation frequency. In other words, the R should to be much greater than 1. The relative velocity becomes approximately equal to omega y cos omega t minus 1 pi, since the denominator is 1. The term pi represents phase lag. So under this specific design condition, the relative velocity of the seismic mass is directly proportional to the velocity of the vibrating body we want to measure. By sensing this relative velocity, we can effectively determine velocity of the vibrating body. Therefore, by carefully selecting the mass, spring and damping coefficient to ensure a low natural frequency compared to the frequencies of interest in the vibrating body, we can create a velocity transducer where the output is reliable measure of the input velocity. This principle forms the basis for many practical velocity measurement devices. Okay, let's have a practical problem now. We are looking at the design aspect of an accelerometer. The problem gives us some key specification of an accelerometer and condition under which it is operating. Our goal is to find two crucial design parameters, that is damping constant and spring stiffness. We are given that accelerometer recorded as an acceleration of measured value it is 9.5 and the true acceleration was 9.81. The solution we are starting by considering this, the ratio of measured value divided by true value, which will be approximately equivalent to 0.9684. This ratio is then equated to a specific expression, that is 1 minus r square plus 2 damping ratio into r the whole square, which is equal to 1 by 0.9684 the whole square. Then this entire thing will become as 1.0663. This represent equation 1. Still we are not solved this. This expression represents the magnitude of the transfer function for an accelerometer relating the output acceleration to the input acceleration. You can see this as a function of frequency ratio and damping ratio. Squaring on both the sides, the reciprocal leads to the value. Let me label it as equation 1. Next, the operating speed of the engine is given as 6000 rpm. Let me convert this into radius per second by multiplying 6000 into 2 pi by 60. We are getting operating speed as 628.32 radians per second. We are also given the damped natural frequency. We are going to convert that into the radians per second, that is 942.48 radians per second. We also know the relationship between damped natural frequency and the damping ratio. Further, we calculate the frequency ratio R by substituting damped natural frequency and this damping ratio. We will get it is 0.667. That is, here from this R and this value we are going to get this. Solving these equations and solving it, we are getting the equation number 2 in the form of R square equal to 0.441 minus damping ratio square. So we are having the two equation. We have to further see and solve it. Alright, let's see the problem once. That is, we were given that accelerometer record an acceleration of 9.5 and true acceleration is 9.81. We started the solution by considering this value and we approximately get the two equations, equation 1 and 2. Substituting this equation 2 into 1, we are getting this quadratic equation. This expression represents the magnitude of transfer function for an accelerometer relating the output acceleration to the input acceleration as a function of R and damping ratio. Now, we are going to choose an arbitrary value of damping ratio. It may be of either 0.7253 or 0.9547. This is a logical substitute. So we are going to see that what we are going to do it and substituting that 0.7253 first time. Okay, arbitrarily we are getting that omega n equal to 1368 radians per second. Further, we already know k by m equal to omega n square. So we can substitute that m and omega n. We are getting stiffness of the spring as 18738 and damping constant formula we are going to use it and substituting it further we are getting the damping constant as 19.8571. So this is very much the arbitrary solution. If we used 0.9547 we will get the different stiffness and damping ratio. It's worth noting that the reason for choosing one value over the other might depend upon the physical constraints or typical design consideration of a accelerometer. For the sake of the solution, we've taken it as 0.7253 and ended with the damping value 19.8571. Finally, I am Concluding this, by using the given information about the accelerometer response to a known acceleration and its dampened natural frequency, we have been able to determine the spring stiffness and damping constant. Choice of one of the possible values, that there may be multiple design parameters that satisfy the given conditions, and practical conditions often guide the final selections. Here we are moving on to another important thing, design of a velometer, that is the velocity meter. The problem here is to design a velocity meter or velometer with a maximum error limit of 1% of the true velocity. We are given the natural frequency of the velometer as 8 Hz and the suspended mass inside the velometer is 0.05 kg. Our task is to determine another necessary parameters such as damping ratio and spring stiffness. Recall the velometer based on a seismic instrument which work best when its natural frequency is significantly lower than the frequency of the vibration being measured. Hence, in this high frequency region, relative displacement of the seismic mass is approximately proportional to the velocity of the vibrating body itself. So, we are using the previous content of the previous slide, that is Z of t R value, and using this equations only we are going to solve this problem. The relationship between the relative displacement Z and base velocity is given here. We want the output which is related to Z also proportional to input velocity. So by substituting this R value into the 1, we are giving the accurate velocity measurement, and also our problem states that the maximum error should be limited to 1% of the true velocity. This means R should be in between 0.99 to 1.01. So we are substituting this equation 2 in equation 1, that is the R value has been substituted, and we are going to simplify it and we are getting this final R in terms of damping ratio. We will see it in the next slide what to do. So as such, from the previous slide we got R in terms of damping ratio and the error also given in the form of 1% in the question itself. We are substituting this error, okay. Then we are also solving the damping ratio equation, that is this equation is we are solving it in terms of R is substituted and we are solving this quadratic equation so that we are getting the damping ratio 2 values as seen in the previous problem itself. So we are going to choose any one of this damping ratio to get our stiffness and the damping constant. So this problem is more or less similar to the first problem, the same thing. So we are choosing arbitrarily 0.755. We are calculating the natural frequency which is already given 80. Just we are converting into radians per second, that's all. By using this omega we are calculating the K, that is mass is given, natural frequency just calculated 502. We are substituting it and we are getting it as 12633. And then the next thing is the final. We are going to calculate the damping. The damping is the formula is given 2 damping ratio into natural frequency into mass. We are substituting all the values which is already given. Only thing is we calculated here this damping ratio value 0.755101. By calculating we found out it is 37.955 Newton second per meter. So based on the design requirement of this problem, natural frequency of 80 Hz and a suspended mass of 0.05 kg, by choosing a damping ratio arbitrarily as 0.755, the solution provides the spring stiffness as this 12633.15 Newton meter and damping constant as 37.9 Newton second per meter. These are the key design parameters. So far, we have primarily focused on the amplitude response of vibration measuring instruments. However, another important characteristic is this phase response. As stated, we all having vibrating measurement instruments. Introducing a phase lag between input vibration signal and output signal we record. Now, if the vibration we are trying to measure consists of not just a single frequency, but a combination of two or more frequencies, a harmonic components like summation of different sine waves, this phase lag can lead to significant problem that is known as phase distortion. The graph of the vibration no longer accurately represent original waveform. The relative timing and shape of different frequency components will be altered. We can visualize this here in this example. We see an input vibration signal y of t, which is combination of two sinusoidal waves sin omega t and sin 3 omega t. The dashed line shows individual components, a lower frequency sine wave and a higher frequency sine wave, that is 3 times its frequency. So here this individual sine waves shown in the form of solid lines, but the dashed line shows the summation of these two, which is the actual vibration we want to measure. Let's assume our measuring instrument, which is introduced a phase shift of 90 degree for first harmonic and a phase shift of 180 degree for third harmonic. A phase shift corresponds to a time lag. For a frequency omega, phase shift of pi radians correspond to a time lag of t equal to pi divided by omega. So the first harmonic with a phase shift of 90, the time lag is 90 divided by omega. For the third harmonic phase shift of 180, the time lag is 180 by omega. Okay. So notice that the time lags are different for the two components because of the different frequencies and phase shifts. Now you can see the output signal of Z of t. Okay, you can see that it is the dashed line, that is the output signal of these two signals represents that. Okay, initially the first one represents sin omega t, that is the original one. Then there is a phase shift, so it is omega t minus 90. Then the third one is omega t minus 180 degree. So the solid line represents the individual signals, the dashed line represents the output signal. So comparing these two waveforms with original and output, we can clearly see the combined signal has been changed. So you can see this is the combined signal, which is the trough and peaks are no longer aligned in the same way as were in the input signal. And the alteration in the waveform due to different phase shift for different frequency components is what we call phase distortion. It means the recorded signal doesn't give us a true representation of the original vibration. Therefore, when dealing with vibrations that contain multiple frequency components, it is crucial to consider the phase response of the measuring instrument as well, to avoid misinterpretation of the recorded data due to phase distortion. Ideally, we want our instruments to have a linear phase response, meaning the phase shift is directly proportional to the frequency itself, which result in a constant time delay for all frequency components, that preserving the original waveform. So we have seen how phase distortion affects a signal with two harmonic components. Now let's consider a more general case. Suppose our vibration signal y of t is a complex wave composed of multiple sinusoidal components with different frequencies, like this. Then when this complex signal passes through a vibrometer, each frequency component will experience its own phase shift, determined by the instrument characteristics at the particular frequency. Therefore, the output signal Z of t of the vibrometer will look like this, with a phase shift, that is pi 1, pi 2 for the individual corresponding frequencies. Notice each component with frequency omega has been shifted by a phase angle pi. So we can put omega 1 means pi 1. The crucial point here is how this individual phase shifts, that is pi of j, are determined by the property of measuring the instrument. For a typical second order system like seismic instrument, which many vibration pickups, the tangent of the phase angle for the jth harmonic component with the frequency of j is given by this formula. You can see the phase shift pi of j not only on the damping ratio and the natural frequency of the instrument, but also on the frequency of the specific harmonic component what we are measuring. So we are considering j omega means related to the instrument natural frequency we have to see. This formula highlights why different frequency component in the input signal experience different phase shifts. The different phase shift among components is what lead to the distortion to the overall waveform in the output signal. So to minimize the phase distortion, we ideally want the phase shift to be linearly proportional to the frequency, which is often approximated over a certain operating frequency range by carefully selecting instrument's natural frequency and its damping ratio. Now let's consider a specific operating region for our vibration measurement. If the frequencies of the vibration what we are measuring, omega, 2 omega, etc., are significantly higher than the natural frequency of the measuring instrument, then the ratio omega by omega n becomes very large. In this high frequency region, the phase shift pi of j for each harmonic component tends towards pi radians or 180 degrees. If pi is equal to phase angle phi for significant harmonic components, that the output signal approximately will become as like this. It is equivalent to minus y of t. This means output signal is essentially an inverted version of the input signal. Key advantage in this high frequency region is that although there is significant phase shift, it's approximately the same for all frequency components. The uniform phase shift simply results in an inversion of the entire waveform. The output record can be easily corrected by simply inverting the recorded signal to recover its original waveform. The relative amplitude and timing of the different frequency components are preserved. For example, simply for a velometer operating in its intended high frequency range, that is omega is far greater than omega n, we can be sure that the relative displacement is approximately proportional to the negative of the input velocity. Again, consistent phase shift across relative frequencies allowing for straightforward interpretation of the velocity. Now consider this acceleration curve. Then the output of the accelerometer which is related to the relative displacement and ideally proportional to the input acceleration as well. The output of the acceleration meter will be, that is z double dot t will be this. Here the phase shift pi 1 pi 2 will depend on the operating frequency omega, which is relative to the accelerometer natural frequency. If the operating frequencies are not significantly higher than the natural frequency, these phase shifts will be different for each harmonic, leading to phase distortion in the recorded acceleration waveform. We have seen the phase different for frequency components having difference lead to phase distortion. Now let's consider if there are conditions under which the phase shift becomes more predictable and less frequency dependent. It turns out that for damping ratio psi equal to 0.7, the phase angle pi varies almost linearly from 0 to 90 degree over a certain frequency range. In this near linear region, we can approximate the phase shift pi as being proportional to frequency omega. If the phase shift phi is approximately equal to b omega, then the time lag t for each frequency component will be t dash pi by omega equal to beta by beta into, since phi equal to beta omega, you can substitute omega will get cancelled. We will get time lag equal to beta, which is independent of a frequency. If each frequency component experiences the same time delay, that is t equal to beta, then the output of the accelerometer will be this one. Here we can rewrite and see that in the second step we see that the output omega square z of t is essentially the true acceleration waveform but delayed in time by beta. If we define a new time variable, it is going to be in terms of psi. It will be named as t minus beta. That is, the output of accelerometer represent two acceleration which is being measured. I am concluding, that is, by designing the accelerometer with a damping ratio around 0.7 operating within the frequency range where the phase shift is approximately linear with the frequency, we can ensure that all frequency components are delayed roughly the same amount of the time itself. In this scenario, the output of the accelerometer represent two accelerations being measured just with consistent time delay, thus minimizing phase distortion of the waveform. This lecture covered the design principles of vibration pickups, including accelerometers and velometers, emphasizing the importance of natural frequency and damping ratio in achieving accurate measurements. We also explored the phenomena of phase distortion that arises when measuring complex vibrations with multiple frequency components and how operating in frequency ranges or with particular damping ratios can minimize these distortions, sometimes allowing for correction of the output signal itself. Understanding these considerations and potential distortions is very much crucial for relative vibration analysis. Thank you for engaging. Your participation is very much important. Kindly go through the lecture videos. I hope this lecture video provided you with valuable insights into the design and limitation of vibration pickup.